for that.
You all ready for some Calc 1? Yes. Yay! I love Calc 1. Calc 1's fun. Hi, I'm McCade.
I'm Caroline.
We're recitation leaders for the math department, but we're here to do CBE 5. Just kind of some docket things while we go through this. If you have any questions that pertain to the presentation, please ask them. Please, all questions are awesome and helpful, but if you have any personal questions, please refrain for asking till afterwards. Additionally, this is recorded. We are not recording any of our faces, but we are recording voices and the presentation. So if you have any problems with that, please feel free to come up to us afterwards. Is that it?
Yeah, that's good.
Cool. Awesome. Okay. CBE 5 covers lessons 14 through 15, aka L'Hopital's. Could be L'Hopital's rule, L'Hopital's law, a bunch of different names for it. Indeterminate forms, antiderivatives, and then initial value problems. So yeah.
Okay, let's do L'Hopital's first. Okay, so when we do L'Hopital's, we're going to jump back to limits for a second. Remember, when we take limits, we are trying to see what a particular function is doing at a particular point. So sometimes we can just plug the value that we want straight in. Sometimes we can't. So L'Hopital helps us so that we can just manipulate it algebraically so that if it's 0 over 0 or if it's 0 over infinity, we can still, infinity over infinity, then we can still figure out what's going on at that point. So that's what this part says. So if we take the limit at the point and it comes out to 0 over 0 or positive or negative infinity over positive or negative infinity, then we can take the derivative of the top, the numerator, and then the derivative of the denominator, and then try putting take the limit of that again and see what we get. So super, super helpful. Let's do a couple of them. Okay, so let's do the limit as this function goes to 2. So first I'm going to just plug in 2 and see what I get. So I'm going to do 2 times 2 squared plus 4 times 2 minus 16. Let's see what that is. 4 times 8 plus 8 minus 16 is 0. So the numerator is 0, and then let's do the denominator. 2 cubed minus 4 times 2. Okay, 2 cubed is 8, and then minus 8 is 0. So we've got 0 over 0, which isn't ideal. So we're going to just take the derivative of the top and then the derivative of the bottom. Can anyone tell me what the derivative of the top is?
4x plus 4.
4x plus 4? Okay, perfect. 4x plus 4. That was great. Drop this power, and then we're just left with just this 4 here. Okay, so we have 4x plus 4 in the numerator. Okay, then what's the derivative of the denominator?
3x squared minus 4.
3x squared minus 4. Okay, slay. Now let's take the limit as x approaches 2 of this. So this is going to give us 4 times 2 plus 4. That's already looking better and not 0. So that's 8. So that's 12. And then 3. So that's 12 minus 4 is 8. Did you guys also get 8? Okay, cool. So now we've got 12 over 8. Or we can simplify that to 3 over 2. Okay, so we get 3 halves at that point. Cool. Let's see. Yes. Okay, we got it right. Kim Cade.
Okay. So just another example. We got the limit as x approaches pi halves of cosine of 2x plus 1 over cosine of x. So first, let's just evaluate the limit. That's going to be cosine of 2 times pi halves. That's cosine of pi. So if we do our little unit circle, cosine at 0 is 1, pi halves is 0. Apparently it doesn't like me writing at the top of the presentation. That's okay. We got -1, and then we got 0. So then cosine at pi, it's going to be this guy. So that's -1 plus 1. And then we divide that by cosine at pi halves, which is 0, which is equal to 0 over 0. So once again, we have one of our indeterminate forms. So that prompts us to take the derivative of the top, derivative of the bottom, and the limit's going to be the same, according to L'Hopital's rule. One kind of just thing that I've seen students mess up on is they do the quotient rule, because they're, okay, derivative, quotient rule. Not for L'Hopital's rule. Derivative of the top independently, and keep that set of derivative of the bottom independently. Then L'Hopital's rule will work. Cool. So that's going to be equivalent to the limit as x approaches pi halves of the derivative of the top. Can someone tell me what that is? Derivative of cosine of 2x. That's going to be
-2 sine 2x.
awesome. So when we take derivative, we took the derivative of the cosine, so that's going to give us negative sine. And then the inside of our trigonometric function stays the same, but then we need to multiply by the 2. That's the derivative of the inside. So that's according to train rule, if you remember that from CBE 3. And then derivative 1 is 0. Okay, and then derivative of the bottom is cosine of x, so no chain rule, just simple derivative of cosine. That's going to be negative sine as well. Awesome. Okay, now that we've taken the derivative of the top, derivative of the bottom, let's see if the limit evaluates. So the limit as it evaluates, now we have sine. So sine starts at 0, and then it goes to 1, 0, and then negative 1. So this is cosine. Cosine, this is sine. Okay, so limit of sine at pi is -2 times 0, and then over negative sine at pi halves, which is -1. So that's going to be 0 over -1, which is just 0. If it was 0 over 0, then we'd have to do the derivative stuff again. But since we just have 0 over a good number that we can divide by, we're chilling, and we're just left with 0, and that gets us a solution of 0. Cool. Any questions on L'Hopital's? Any at all? Awesome. Okay. Indeterminate forms. So these are any sort of form that, like, at least to mathematicians, when you see one of these, there's actually kind of like multiple things that could end up being, so that it makes their evaluation indeterminate. We don't know what it actually is. So the ones that we just saw earlier were 0 over 0, or infinity over infinity. That's a terrible infinity. There we go. Or there's also multiple. Some common ones that you're probably going to see while doing some of this L'Hopital's rule stuff is 0 to the power of 0, infinity to the power of 0, and then 1 to the power of infinity. So it's just when we're doing all these limit stuff, there just happen to end up being these indeterminate forms, and doing some little different math manipulations, you can actually get different answers when you try to manipulate it. So that's why we call them indeterminate. And it's just whenever you evaluate these limits, if they go into that, it may or may not still exist. So cool. And more specifically, you get these 3 when you evaluate a limit like limit as x approaches a with a function to another function's power. Cool. So, solving for indeterminate forms. With our 0 over 0 or infinity over infinity case, it's just like normal L'Hopital's rule. But whenever we have one of these different forms, like this 0 to, or like something to a something power where it's indeterminate, we actually have to do one of these different things. So, we have to, or at least according to L'Hopital's rule, we need to have some sort of f of x over g of x kind of form, but those others aren't in that form. So if we get one of those indeterminate forms, we have to change it back to somehow looking like this to apply L'Hopital's rule. So we can only use L'Hopital's rule when we have a quotient of 2 functions. That's our f of x over g of x. And then for the first 2 indeterminates, we can normally or usually rearrange some of these functions so that they look like f of x over g of x. And then once it's written as a quotient, then the limits evaluate to 0 or infinity, then we can use L'Hopital's rule. Awesome. So for indeterminate forms, like the limit as f of x to the power of g of x, we want to raise it to the power of e. And then in the power, have ln our thing. Because we're going to use some log properties, and you'll see in a second. But whenever we add or subtract or input any sort of like function, changing the function, we can't actually do that. We have to make sure it equates to the same thing. So that's why we need to, that's why we need to do it to e to the ln. Because those two will cancel out, but it also allows us to do some of our manipulations. Cool. So once we do e to the ln of some f of x to the power of g of x, then we can use some log properties. We can pull this g of x down, and then we can change it into some sort of 1 over g of x, possibly, in our power. That's now what looks like our L'Hopital's rule. And then we can start to apply it. Cool. So, did you want to do this one, or?
You can do it.
Okay. Problem number 3, determine the numerical value of the limit of x approaches 0 to the right-hand side of 7x to 4x. Or, yes, to the 4x power. So, like any limit, let's just evaluate it, see if it ends up being indeterminate. So, 7x, when evaluated at 0, is 0. And then 4x evaluated 0, 0. Boom, that's one of our indeterminates. Okay. So, we need to do this e to the ln kind of stuff. So we need to change this limit as x approaches 0 to the right-hand side of e to the ln of 7x to the 4x. Because that will keep our function the same even though it looks different. So now that we've done that, we can change this into the limit as x approaches 0 to the right of e to the, according to our log properties, if we have something to the power of something, we can pull that power out in front as if it was multiplied. So that's going to be 4x ln of 7x. Okay, how could I change that into looking like a quotient? Any thoughts? Or at least the power. Don't look at the e, but at least the power. How could I change that to look like a quotient?
Get the derivative.
Not the derivative yet. We still need to put it into our quotient. But if we're multiplying by 4x, if we divided by 1 over 4x, would that be the same relatively? And that would put it into our quotient because we're dividing one function by another function. Cool. So that would be e ln of 7x divided by 1 over 4x. And now we're in our L'Hopital's kind of like quotient that we want. So now I am purely going to focus on this power. I'm going to ignore the e for now, and I'm going to look at the power. And the power looks like something I can do L'Hopital's. So let's do L'Hopital's for it. So the power, it's going to be derivative of the top. What's the derivative of ln of 7x? It's going to be 1 over the inside of our function times by the derivative of our function. So it's going to be 1 over 7x times derivative of 7x is what? 7. Okay. And then divide it by the derivative of the bottom. I can also, again, rewrite this as 4x to the negative 1. And then I just apply a power rule. So drop the power, negative 1 to the 4x minus a power, and then divide it by the derivative of the inside, which is derivative of 4x. 4. Cool. Now this is in our L'Hopital's form. But if we were to apply our limit right now, so e limit as x approaches 0 to the plus, we're going to get something that's to the line of e to the 0 over 0. That's gross. So we need to manipulate this in a little bit. So let's see if we can simplify this power. We have a -2 on the bottom, meaning that on the top, it would be 4x squared. And we also, these 7s would cancel, so we're left with 1 over x, or x to the -1 on top. So this simplifies to e to the x to the -1 over, that'd be 1/4, -1/4 x to the -2. I would say we can switch both our x to the -1, switch it to the bottom, so that'd be just a solid x on the bottom, excuse me, and then our x to the -2, switch that up top, so it's just regular x squared, so that's going to be e to -1/4 x squared over x. One of those x's will cancel, and we are left with the limit as x approaches 0 from the right of e to the -1/4 x. That looks a lot more simple than it did previously. Now let's apply that limit. That's going to be the limit as x approaches 0 of e to the -1/4 x. So that's going to be equal to e to the -1/4 times 0, which is equal to e to the 0. Except for 0, what is anything to the 0 power?
1.
1. So that is equivalent. I'm going to do a little squiggle. That is equal to 1. That's a lot of work just to get to 1. But it needs to be done, unfortunately, if we want to get the correct limit. So, any questions? That was a lot of manipulations. So, if any questions at all, any step in the process, feel free. Okay.
Okay, so now we're going to be talking about antiderivatives or integrals. I don't know, do you guys be calling them integrals or you call them antiderivatives?
Either one. Yeah,
Okay, cool. We be doing antiderivative integral stuff. Okay, so remember, yeah. Okay, so what's an antiderivative? Okay, so we can kind of think of like the integral is kind of the opposite of the derivative, like that's kind of how we move between the two of them. So when we're taking the derivative, we're kind of finding like the slope at like a particular point. We're like, oh, what's the slope at that point? But when we go backwards, we're finding the area under the curve. Okay, so hopefully we're all a little bit familiar with the process of how to do an integral. A little bit. Does anyone not even remember how to do an integral? Okay, it doesn't matter. We'll go slow. Okay, so here's some of the common integral like forms that you need to know. These ones pop up like pretty frequently all over the place. So yeah, and then since we don't have bounds here, like we don't have a particular A and B point that we're going in between, we always need to add that plus C at the end of them. Okay?
Can I touch on that?
Yeah, go ahead.
I would say the most important ones that you will see on any and all on any and all tests are the ones I have underlined right there.
Yeah.
Those are the most common ones you will see. You're going to see them in every class that you take of calculus after this. The ones that aren't underlined are kind of the more niche ones that you might see every once in a while, but the ones that are underlined are like your guarantees. So take real big note of those guys.
Yeah. Okay. So let's do this problem. So in integrals, well, when we take an integral of like two things added together, we can just like we can take two separate integrals and then add them together at the end. So that's what I'm going to do because it keeps it simpler and like more organized in my head. So I'm going to first take the integral of 5 over x, square root of x. dx, and then I'm going to do a separate one for 7 to the 4th root. We'll just to the 4th root of x to the 3rd dx. Okay, so let's do this first one. First, I want to get all of those weird powers in the denominator like together. So I have x to the power of 1, and I also have x to the power of 1/2 on the bottom. And since those are multiplied by each other, I can just add the powers. So now I have 5 over, and then 1 plus 1/2, 3/2, x to the 3/2 dx. Okay. Another thing that I can remember is that when I have a power in the denominator, if I want to like get rid of the denominator, then I can move the power to the numerator and just make it negative. It's like that's the exact same thing. So this is also equivalent to 5x to the negative 3/2. So I haven't even taken the integral yet. I'm just like simplifying this so that it's just less work when we actually do take the integral. Okay, but now we are ready to do it. So we have one of these forms that we were talking about before. We have this one. So I'm going to add 1 to the power and then divide by the power. So when I add 1 to the power, I go from negative 3/2 to negative 1/2. So I have x to the negative 1/2. And then I need to divide by the power. So I have 5 over negative 1/2. Okay, so that looks better. And I guess technically I have the plus c. I'm going to simplify this more. So does anyone know what 5 divided by 1/2 is? Negative 1/2. I'm going to do 5 times, and then I'm going to flip that. Negative 2 over 1. So I have negative 10. So I have negative 10 times x to the negative 1/2 plus c. Oh, and that's just the same thing as negative 10 over the square root of x plus c. Okay, so now we have this first term. So now let's do the second integral here. Okay, this one, it's already looking pretty simple. I'm going to simplify the powers even more. This 4th root, I can turn this into a fraction. And in my mind, I always remember that the denominator goes on the bench, like that little bench thing on the square root. Is that how you remember it?
No.
The bottom goes on the.
Divide by roots. You.
Oh.
Numerator's powers.
Oh. I always be thinking the bottom goes on the bench. So I'm like, okay, so that
like
the 4's in the denominator. Yeah. Okay. So now I have 7x to the 3/4 dx. Okay. So I'm going to add 1 to the power and then divide by the power. So I'm going to go down here. Oh. So I'm going to have x and then 3/4 plus 1. It's going to be 7/4. 7/4. And then I'm going to have 7 divided by 7/4. And that's the same thing as 7 times 4 over 7, which is just 4. So now I have 4 times x to the 7/4 plus c. So in the end, like both of them have that plus c. I mean, we just need to have a constant at the end. So I'm going to have negative 10 over the square root of x plus 4x to the 7/4 plus c. I guess I just did a bigger c because I just did 2 of those smaller c's. It doesn't really matter. Plus a constant. Okay, answer. Yeah, that'll do. Okay, cool. Oh, yeah.
Okay, so evaluate the integral of x squared plus 1 multiplied by 3x plus 4. Do you guys think of any possible way that we could do this without simplifying? At least at this point, no. So we're going to simplify the expression. So we're going to, that's going to be equal to the integral of, first, that's going to be 3x cubed. Second, it's going to be plus 4x squared. Then we got plus 3x. And then we got plus 4dx. Awesome. We could do 4 separate integrals of 3x cubed and then 4x squared and then 3x and then 4 and then just add them all up. Or we can just do it all at the same time. I'm personally going to do it all at the same time. So our new expression after we take the antiderivative of each of our parts, since they're separated by a plus or a minus sign, is going to be the antiderivative of this. That's going to be 3x cubed antiderivative. Or you can think of it as what, when I took the derivative, equals 3x cubed. In this case, with our little cheat sheet that we had before, we're going to add 1 to our current power and then divide by that new power. So that's going to be x to the 3 plus 1, which is 4 of 3. And then we divide by this new power. That's going to be a 4 on the bottom. Okay. And then we have this guy that is add a power. So that's going to be x cubed times 4 divided by the new power. That's 3. Then we add a 3x. We again add 1 to the power. So x to the 1 is x. So then x1 plus 1, that's going to be x squared over 2 because we're dividing by the new power. And then whenever we are taking the integral of a constant, we're just going to add an x up front. So that's going to be plus 4x. And then lastly, plus our constant. Because there could be like this secret 0 out front that when we take the derivative of this new function, it went away. And that's why we add this arbitrary constant. So sometimes that could be 0. Sometimes there isn't that arbitrary constant. Sometimes that could be 1,472,000. So just something a little to think about. And we are done. Any questions on that? Okay. At least for this point in the class, if you see like something nasty up in here and you're like, shoot, I don't know how to take that integral, see if it simplifies. If you can get it simplified, you're going to be able to take the integral. So.
Okay, cool. Let's do one more of these integral problems, and then we'll move on to the next type of problem we're going to do. Okay, so I'm going to split this up again like we've been doing. I'm going to do 2 separate integrals. So I'm going to do the first one of -2 sine of 4x dx, and I'm going to do the second one, 3e to the 3x dx. And I'm just going to end up adding those. I'm just going to add that so that I do not forget to add them at the end. Okay, so does anyone see something that I could do here? Do they know what U substitution is? Do you guys know what U substitution is?
No. What? It's unfortunate because it's actually really weird. They don't teach something like that for when they're doing e and sine, like trigonometric functions. They don't teach chain rule when they're first doing the derivatives of those. They just expect them to do it. So it's really weird.
Okay, great. So how would you guys go about doing a problem like this?
I can give a little thought process if.
I have an idea.
You're you did the same thing that I did.
Just think about what would have that as the derivative.
Yes, exactly. So like if I had let's just say I had sine of 2x. If I took the derivative of that, like I have to do the chain rule. So I have to first take the derivative of the whole thing, which would be cosine of 2x. Then I have to multiply it by the derivative of the inside, which is 2x. So 2x, so I have to multiply it by 2. So when I'm taking the integral and I go backwards, do you see how this 2 disappears? Like we just don't need that 2 because when we take the derivative of the inside and it appears. When we go backwards, the derivative of the inside does not need to be there anymore. So we need to take it away. Okay, so for this problem here, the derivative of the inside, so my inside function here, which is 4x, the derivative of the inside is 4. So when I go backwards to take the integral, I need a 4 to disappear. So I'm going to do my favorite thing, which is multiply by like my favorite flavor of 1. So I'm going to multiply the inside by -2. So I'm going to multiply the inside by -2. And I'm going to multiply the outside by -1/2. Because when I have that -1/2 and that -2, when I multiply them together, it's just 1. So like I really haven't done anything, but like I'm getting what I want out of this expression. Does that make sense? Because then this -2 and this -2 turns into a 4. So I get 4 sine of 4x. And like when I'm going backwards, so like back up here, like now I have the derivative of the inside. So like it disappears when I go backwards. Does anyone have any questions about that? Sometimes this concept's hard to grasp.
At least the first couple of times.
Yep, the first couple of times. And then once you start doing it, you're like, oh my gosh, that's amazing. So, no? Okay. So now I'm going to take the integral of this. I've got this -1/2 out on the side. Okay, so first of all, that 4 is going to disappear. So I'm just going to yoink it out of there, say you are gone, or taking the integral, so you need to disappear. So now I'm just going to deal with, like, what's the integral of sine of x?
Cosine of x.
Yes, it's going to be negative cosine of x. Okay, so perfect. So I'm going to have negative cosine, and I'm going to keep that inside function the same, 4x. And then I'm going to still multiply it by that 1/2. Oh, -1/2. Okay, so that's going to give me 1/2 cosine 4x for this one. Okay, any questions about that? Okay, let's do the 3x. E to the 3x. Okay, so this one, we're going to do the same thing. Because when I have e, let's say when I'm taking the derivative of e to the 2x, I get 2e to the 2x. So when I need to go backwards to take the integral, the derivative of the inside needs to disappear. So the derivative of this inside function is 3. Oh, that is so convenient because this 3 is just going to disappear then. I'm going to end up with e to the 3x. So I'm going to add those two together. 1/2 cosine 4x plus e to the 3x, and then I'm not going to forget that plus c. And that's what we get here at the end. Okay, let's see if that matches. 1/2 cosine 4, okay, word. Okay, any other questions about that? All right.
Cool. So initial value problems are what we do when we want to solve for this plus c. We're given some sort of base information, so we're given some sort of derivative, and we want to find what its antiderivative is, and then we have some sort of initial condition that we can then solve for to then find out what that plus c originally was. So first, we have to find the indefinite integral, and then find the plus c, and then we have to set it equal to whatever we're plugging in that function at some point. We set it equal to what it is equal to, and then we solve for c. So, long story short, we got f double prime of x is equal to 6x plus 3, and then f prime at 0 is equal to 4, and f of 0 is equal to 7. So, once we find f prime and f, we'll be able to evaluate these at those points. But first we need to find those, aka we need to find the antiderivative of f double prime. So, f prime of x is equal to f, the integral of f double prime of x dx, which is equivalent to the integral of 6x plus 3 dx. And that's going to be equal to the antiderivative of 6x. We're going to add the power, divide by that power. That's going to end up being 3x squared. And then derivative or antiderivative of 3 is 3x plus c. So we get some sort of f prime of x is equal to 3x squared plus 3x plus c. But we know that f prime at 0 is equal to 4. So we're going to plug in f prime at 0. That's going to be 3 of 0 squared plus 3 times 0 plus c, which is equivalent to 4. That's 0. That's 0. This statement ends up saying that c is equal to 4. And just to add some more, I'm going to put this little subscript of C1. Just because we're going to do another one of these problems, and I don't want to mess up these plus C's, I'm going to end up calling the next one C2. Just so we can differentiate between the two. Cool. Let's do it again. So now we have our f prime of x, which ended up being f prime of x, just like store it somewhere that's kind of out of the way, which is equal to 3x squared plus 3x plus our C1, but we just found out that C1 is equal to 4, so we can replace that. It's 3x squared plus 3x plus 4. And now we need to find f of x. F of x is equal to the integral of f prime of x dx, which is equal to the integral of 3x squared plus 3x plus 4 dx, which when we take the integral, that's going to be add a power divided by that power, so that's x cubed, plus add a power divided by that power, 3x, or 3 halves x squared, plus add a power divided by that power, which is 4x, and then plus a different constant. If we just put a bunch of c's everywhere, you might get confused or you might mess up. So it is kind of good to either call it a different kind of c. You can use any variable. Sometimes you'll see professors use a k, just something that represents some arbitrary constant. And at least in, don't look at that. At least in this case, I'm going to use C2. C2. Okay, so now f of x is equal to 3, or x cubed plus 3 halves x squared plus 4x plus c2. We then plug in our f of 0, which we say is equal to 7. So that's going to be 0 cubed plus 3 halves times 0 squared plus 4 times 0 plus c2 is equivalent to 7. That's a 0, that's a 0, that's a 0. We now have c2 is equal to 7. And now we can finally say f of x is equal to x cubed plus 3 halves x squared plus 4x plus our c2, which we just found out to be 7. Cool. Are we done? Unfortunately not. I'm going to spoil it. We need to find f of 2. So let's just plug in 2 to what we found for f of x, see where it gets us. So that's going to be f of 2 is equal to 2 cubed plus 3 halves 2 squared plus 4 times 2, little parentheses around everything, plus 7. Okay, 2 cubed is 8 plus, one of those 2's will cancel, so we're left with plus 6, plus 4 times 2 is 8, plus 7. And if you were looking earlier, that was already spoiled to what the answer is. That's going to be 16 plus 6. That's 22 plus 7, which is 29. F of 2 is equal to 29. Any confusion on the process? Okay. Feel like if you saw a different one of those, you could replicate it on your own? Awesome. Cool.
Okay, let's do, this is our last question. Okay, so so we gotta find f, or we gotta take, we're gonna end up taking two integrals here. We've got f double prime, we gotta get back to just f. So first I'm going to take the integral of this, of 3 sine of x minus 4 cosine of x dx. Okay, the integral of sine, that's going to be negative cosine. So I'm going to get negative 3 cosine x from this term. And then the integral of negative 4 cosine is negative 4 sine. Okay, cool. And then I've got that plus c. Okay, so now I'm going to solve for, and this is my f prime. F prime of x. Okay, so now I've got that f prime of x. Yeah?
Why would it be negative 4 sine and not 4 sine?
Then, so why did I keep the 4?
Well, you kept it at negative 4. Why not a positive?
Okay, so when I take the derivative of, sine of x, what do you get?
Derivative?
Yes,
Cosine.
cosine of x. Okay, so if I take the integral of a positive cosine, I'm going to get positive sine. So like if I'm going backwards like that. So if I take the integral of a negative cosine, then I'm going to get a negative sine.
Yeah.
Okay. Okay, perfect. So now I'm going to solve for f prime of 0. And that needs to be equal to 2. So I got negative 3 cosine 0 minus 4 sine 0 plus c equals 2. So I know that sine of 0 is going to be 0. And then the cosine of 0 is 1. So I'm going to get negative 3 plus c equals 2. And then when I solve for c equals 5. Perfect. So now I know that my f prime of x is equal to negative 3 cosine x minus 4 sine of x plus 5. Okay, so now we've got to do it one more time. I'm going to find f of x, I gotta take the integral of negative 3 cosine x minus 4 sine of x plus 5 dx. Okay, what's the integral of negative cosine? That one should be negative sine, right? Does everyone agree with me? Okay. Negative sine of x. Oh, I gotta keep my 3. Okay. And so then the integral of negative sine.
It's positive cosine.
Positive cosine, perfect. And then, the integral of a constant, I'm just gonna tack on an x, 5x. And then I've got that plus c. Cool. So now I have my f of x, but I don't want the plus c, but I do have this f of 0 equals 2. So I'm gonna do f of 0 equals negative 3 sine of 0 plus 4 cosine 0 plus, and then 5 times 0 is just 0 plus c equals 2. Cool. Okay, so sine of 0, we already know is 0. So I've got 4 cosine 0, which is 1. Oh, sorry, 4 cosine 0 is 1, but then times 4 is 4. Okay, and then plus c equals 2. So c equals 2 minus 4 is negative 2. Coolness. So now I know that my f of x equals, dang, I've been writing this so many times, negative sine of x plus 4 cosine of x plus 5x minus 2. Okay, and we're not done yet because we have to find f of pi. Okay, negative 3 sine of pi. Does anyone know what that is? That's going to be 0. Cool, 0. And then plus 4 cosine pi. That's going to be negative 1, and then times 4, so negative 4. Perfect. And then we have plus 5 pi minus 2. So that's going to give me 5, I'm going to write it over here, 5 pi minus 6. Boom, there it is. Answer. Okay, right there, slay. 5 pi minus 6. Okay, work. Any questions? Okay, so this should hopefully cover a lot of the material that's going to be on CBE 5. If you have any questions, we can answer them, like specifically if you have like a practice problem or something, or we also have the tutoring center just in that other room. I'm going to post this video on YouTube shortly. We also have like the previous year's videos on there too. Cool, so that is the end of the CBE review. Thank you for coming.